We're going to talk about habitable planets.
Cool.
Okay.
Like science fiction.
No, actually not. I don't need science fiction. My reality is like a science fiction. So what I need science fiction? I'm better than the science fiction, the reality.
Does the Drake equation define some sort of roadmap for astronomers in their quest for understanding our universe, especially when you read the equation from left to right?
No, I think the Drake equation is based on a very simplistic perception of life like we are on Earth. And the problem of the equation, it's only relevant for the SETI experiment, which means you look for life as it is today on Earth on a global statistical way. If you look at the history of life on Earth, most of the time it was invisible. So I think the Drake equation is targeting the wrong public. It is giving a very nice simplification in a way that you can build up a program like SETI looking for radio signal. But right now, it is not at all the way the people are addressing the problem. It's clearly not about the number of stars and number of planets or blah, blah, blah. So we know all this. I mean, there's planet everywhere. So it's an irrelevant problem. The question that you ask here is, what defines a planet that can sustain life? You have two ways to do that. You can be lacking creativity, and that's the Drake equation, which practically relates to the Earth. Or you can try to be creative and say, well, maybe there is plenty of planets that are different than the Earth that can produce life. And maybe the life that can produce this planet is different. When I mean different, it's still chemistry, but it's just another kind of chemistry. And then life may be not just visible, because it's almost invisible. Maybe there is life on Venus, maybe there is life on Mars. I'm not very good at finding them right now, but maybe there are, because we're not looking at the right stuff. From what we know about the diversity of the planetary system right now, I think we should assume as a fact that given the diversity of the planet, it is likely to have an extremely high diversity of chemistry going on. Whether there is a hope that this diversity of chemistry is leading to life, that's open to debate, but that's something that can be tested. It's a chemistry experiment that needs to be done, is what is the origin of the chemistry of life on Earth, and how far could you divert from this chemistry on Earth to make another chemistry that leads to something that looks like life. So in that sense, I think the Drake equation doesn't tell you anything at all.
What do you think of the SETI program?
Okay, the SETI program is targeted to a very specific question, which is, could you find what's called a civilization on the base of the signal they produce? So it's mostly radio signal, but it could be also light signal, whatever. I think in science, there is no limit. If people believe this is what they want to look for, I think I'm very happy for them to do that. The problem I have with that program is I would never do that, because I think it's an extremely frustrating program, because you learn nothing by the null result. And when you do a physical experiment, you really have to acknowledge the null result. So the null result should tell you as much as the result. So to me, it's a quest, and that is looking for something that you have an idea of. I think it's a beautiful quest, because I can understand the myth behind, I can understand the impact that you have on the quest. But if you find nothing, you still have the same situation. So when you look for planet, you detect planet, you ask the question about the origin of life on this planet, you measure the chemistry of this planet, you understand something about what's going on in terms of chemistry or geochemistry or cycle of the chemistry and possible imbalance, you have chemistry imbalance on the atmosphere. Whatever it is life or not, you understand about the minimum conditions you have on these planets, and then you can start elaborating what is the likelihood to build on life. Well, the other problem I have with the SETI is, let's imagine there is a civilization of fish. I don't know how you're going to talk to fish. So the people looking for SETI, they should first try, jellyfish. They should try to first to design, okay, there is a population of jellyfish. Who are going to talk to that? Let's try to do that already on Earth. Let's take a couple of jellyfish and exchange some information. Let's try how you can do that. That's exactly the kind of problem they're facing. So I understand the vision of the 60s. I love it because it's an easy try. So it had to be tried. And it's easy, you can point to 100 stars, you can look at radio telescope, and if this is obvious, it will pop up. So people have been looking to a lot of stars right now. Whether they should be continue or not, I think again, it depends what you really are looking for. But at the end, even if they do 1 billion stars and they got nothing, what did they learn about life in the universe? Nothing. They just learned that there is no life which is exactly like us producing a signal at the time they got the signal measurements, which is right now. It doesn't mean that in 1 billion years old there will be a signal produced on and maybe life. It doesn't mean that maybe there were life on that planet before and it should just come too late. So that's a bit of a difficulty I have with the SETI right now. But if there are people doing it, I'm always curious to hear what they're doing. So I think it's part of science, the diversity of the science.
Can you tell us about your work that you've done in collaboration with a group at the LMB here in Cambridge, where you talk about the origin of RNA precursors and exoplanets?
Okay, so right now we're trying to define the way to make progress about the origin of life on Earth and also the possibility of life on other planets. There is a lot of discussions, what is the best way to move forwards. But there is a couple of elements we all agree on, which is first, I think when you look for the origin of life on Earth, there is a limit in what you can get because, we have no memory of the past on Earth. There's no way to understand anything here, except that to look at what is the current structure of life. But it is also understood that when you look at the current mechanism of life, this is an extremely evolved mechanism. And if you take an example, if you want to look at the first steam engine and you want to look at the last version of the steam engine, there have been so much progress. So life has optimized itself in a way that the life as it is today, there may be some stuff that is related to the primordial element that was kind of a living, but maybe it's almost invisible to it. So we decided to go as back as we could, and we decided to start on the very basic element, which is there is a limited number of amino acids, very specific, that life is using. And we asked ourselves, okay, can we start from that to define what are the conditions for life? And that's kind of going to the simplest possible assumptions. It doesn't mean that when you have the amino acid, you're going to get life, and nobody has really connected the dot yet. But there are people working on that, and I'm pretty much optimistic that at some point in the lab, people on Earth will be able to do that, trying to assemble the amino acids in a way that they produce some kind of replication mechanism to evolve with life. But then we look at this and we ask the question, could you do the chemistry? Could you do the Earth science conditions? Could you imagine a planet? And how does it work? And we found out that you could use the light from the star as an energy trigger. So we look at the possibility of light from the stars. We try to measure that. We compare with the lab with the chemistry. We did chemistry experiment by bringing astrophysics light in a way, not just a lamp, but just light that is calibrated properly. And this is all the kind of connection we're trying to do right now. And that's the way the field is trying to evolve, is trying to bring different piece of knowledge together, which the astrophysics knowledge about the planet and the atmosphere of the planet, the geophysics knowledge that you get from Earth, the planetary system on our inner systems, and also how far could you learn about plate tectonics, about volcanic activity, about magnetic field on these exoplanets. And this is part of the equation. Some people assume that you need absolutely plate tectonics to recycle the carbon. If this is the only way to recycle the carbon, I guess we need that. Otherwise, we end up like Venus. Venus may have looked like the Earth 500 million years old ago, because Venus was experiencing some kind of plate tectonics recycling. If you imagine the first inhabitant on Earth looking at Venus, they would have seen a kind of blue planet as well. And the plate tectonics stop, and then there is a recycling, and then it's a greenhouse effect that you just never stop. So all these elements are very interesting, and we can study them by combining all this field. So that's the approach we have started here. We're not the only one. I mean, there are a couple of people in Harvard, and there is a global initiative which is supported by Simons Foundation right now, which is trying to connect all this together, which to me is extremely interesting. And I'm trying to promote the idea and hoping that this Nobel Prize will help my voice to be heard, that we are building a new field. Because we are facing what's called the red type effect, a bureaucratic effect, is if you are an astrophysicist and you want to ask for money to do a chemistry experiment, you can't, because the astrophysics panel will tell you, well, this is astrophysics, you should ask to chemistry. And the chemistry will tell you, oh, but you are an astrophysicist, you shouldn't ask for us. So he has no more funding. There's nowhere to promote. And that's the kind of the challenge when you do science between different scientific topics that usually are completely divided. We don't even have the same council for science between astronomers and people doing chemistry. So this is really the challenge right now, is how can we assemble a sensible critical mass of people that will be able to operate together and come up with a real roadmap. So I don't think we have a clear roadmap right now, but there's a lot of elements which is interesting, which is related to, let's try to go to the most basic element of life we find in the current life, to find the conditions on other planets, and then possibly explore deviation from that. So if you don't have the same chemistry, could you trick a little bit the chemistry and still having something which may be different amino acids? There may be some similar, but not maybe exactly the same. That will work as well. And then you may end up with a different kind of life, which is based on a different functioning mechanism, but that at the end leads to the same kind of global life kind of mechanism. And I think this is the adventure we are now embark. And I'm pretty optimistic that given all the effort, all the brains, all the tool we have, and that we should get closer to an answer. And it may take 100 years still. In terms of science, is nothing really. So that's the kind of life roadmap that I would see, while it's not yet clearly defined.
In 2016, you discovered exoplanets orbiting a star called Trappist-1.
Yeah.
What do we know about the system?
Well, that's a great work that I did with my Belgian colleague, and Michael Gillon is the leader of this exercise. I think this is fascinating because we're trying to trick the system here. We're using smaller stars, cool stars, it's called M stars, to compensate the fact that we have not found a true Earth, but we have plenty of Earth very close. So the idea is, if you look for an Earth-size, Earth-mass object very close to a star, and you want that planet to be potentially habitable, you need to make sure the planet is not roasted by the stars. So by cooling down the stars, looking for low mass stars, you have the right distance to have the same kind of flux coming from the star. So we found Trappist systems, and there's 2 or 3 planets which are clearly like the Earth in terms of Earth mass, Earth size. And they are within this region that we call the habitable zone. So it means it's a region where if you take the Earth like it is, you can move it in and out the orbit, and you still maintain the water. Well, the assumption is you have the same kind of atmosphere, same kind of geophysics, which we don't know at all about the system. But it gives you some boundary conditions. There is a real interest right now to go a little bit deeper about these planets and to try to detect the atmosphere of this planet. There is a couple of possibilities here. First, the fact you have a low mass star, they have a different kind of radiation. It's in a way that the star is very active when the star is young, and the sun slows down very quickly, and then it becomes pretty nice in a way. You still have eruptions and still time to time, but not too much. The M stars is very different. They took a long time to cool down, and there's a lot of activity, a lot of X-ray. So you don't really like M stars because of this. So there's a lot of high energy particles. It's not very clear whether an atmosphere will survive, but let's find out. Assuming the atmosphere would survive, what exactly would look this atmosphere? Because we're talking about another kind of stars, the planet is very close, so nobody really knows very well about this. But again, let's have a look. And we have a James Webb Space Telescope, and that certainly could do something. The ambiguity of this program is if the atmosphere is very thick, like for example 200 or 500 kilometers, we're going to find out. This will be detected by the James Webb. If the atmosphere is like the Earth, 10, 20 kilometers, we're not going to see anything. So we should be able to tell whether there is a big atmosphere which in this case, it doesn't look really that much like the Earth because we don't have 500 kilometers atmosphere on the Earth. Then we may detect that there is no atmosphere detected, which doesn't tell that there is no atmosphere. Just say we have not detected anything. We could still have a 10 kilometers atmosphere or no atmosphere at all, like on Mars. So Trappist is an interesting system because if you detect something, you can reject almost life on it. But if you don't detect something, there is still the hope that there is life, and you're waiting for the next generation of instrument to just do even better. So it's very kind of the science building up on the past. So it's a fascinating system. There may be others. We're looking for other of that kind that you can study. And who knows, the kind of surprise that we're about to find. I think it's great because for the first time, we can really try something and we can at least get some data. It's not about talking about imagining something. We have the target, we have the tool, let's find out. And I think it's a fantastic adventure that we're living right now.
The closest potentially habitable exoplanet is the Proxima Centauri b that was discovered in 2016.
Yes.
And if we decide to send a probe there,
yes,
with our current propulsion systems, it will take some 50,000 years.
Yes.
So what are the most viable candidates for new propulsion systems that are currently under study?
Well, I don't really like this idea of sending a probes. I think it's a sci-fi dream, and I think it's misuse of the money right now. You can study a lot of stuff just by looking. So I think we should be much better to design the kind of equipment we would like to build to try to retrieve as much data we can before sending a probe. I think we are 100 years behind sending any probe at that distance. And even if you want to send a probe with the current technology, I think in 10,000 years, we should reach the technology to go much faster, and we still have this old probe on its way while the time you will move the new one. So I think we should really get a bit more focus. I know there are some people that would dream about that. There is some private sponsors that would like to do that. I personally regret that they're not talking to astronomers about this, because I love the idea to look for life on Proxima. It's a very good program, but not sending a probe. Just build the equipment to just look at it. And we should be able to tell a lot already without going. Now, if you want to go there, the problem you have to face is you better go quick, because otherwise it takes too long. So the speed has to be quite significant. So when you start reaching 1% of the speed of light, the mass becomes bigger. So how are you going to slow down that stuff? I mean, if you just have a kind of flyby 1 second to the planet, what's the purpose? So I think we should try to engage better with the people that would like to have this program, and I would really invite the people that are interested by this, and especially from the private sponsor side of you, to talk to astronomers and try to come up with a realistic program. And this idea of sending a probe to Proxima, I think it's just a dream right now, and we should not spend money. You can still dream, that's fine, but spending money to that is just a mistake to me.